Okay, I think we can go ahead and get started. Thanks everybody for coming to this. I'm James Wilcox. I work at Certora on education and language design, and I'm also a lecturer at the University of Washington in Seattle, where I teach programming languages and program verification. So today we're going to talk about inductive reasoning in smart contracts. So we're going to talk a lot about induction, which is one of my favorite topics. In fact, I'm teaching a class right now at UW about programming languages where we talk basically only about induction. So I'm excited to also be able to kind of talk about this stuff with you guys. So you may not have heard of the kind of induction that we're going to talk about today, but it's very related to the kind of induction that you probably have heard of. And there's some other kind of machinery that I want to show you, ways to think about problems in the smart contract space that allow you to apply the ideas of induction to prove your programs correct. And one of the key kind of insights that we're going to talk about today is that a property about your program might be true despite the fact that it's not going to be what we call inductive. And so you're going to have to strengthen that property in order to prove it. So to get started, let's talk about the kind of induction that we all might be familiar with from maybe like a math class of some kind at some point in your life. This is sometimes called mathematical induction. And this is just the idea that if you want to show that a property is true of all natural numbers n, then you can show it for 0. And you can show that whenever it's true for a number m, it's also true for m plus 1. Okay, so maybe let's take a second and be philosophical. Why is it that mathematical induction works? Like, what is it about this technique that allows you to prove something about all numbers? I guess one way to think about it is if we draw a number line down here somewhere. So let's say we've got all of our numbers, zeros over here somewhere, and we want to know that, let's say we're trying to prove that P of n is true. Okay, well, if we want to get to a proof of P of n, then these two steps, prove it for 0 and prove that if it's true for a number, then it's true for the next number, allows us to basically build up a proof of P of n step by step. So we can just use this almost like a program, right? Almost like an algorithm for computing a proof of P of n, because we start by computing a proof of P of 0 using the base case. And then we use the inductive case to transform that into a proof of P of 1, which we then transform into a proof of P of 2 and a proof of P of 3, and so on, all the way up until we get to whatever number we're looking at, right? So no matter what number we care about, we can just iterate this second step that many times, basically, to get a proof of that fact. Okay, and like this is pretty obvious and simple, and you may have seen it before, but I think there's actually something kind of deep happening here, because we are proving like an infinite number of facts with a finite amount of work, right? There are infinitely many non-negative integers, and yet we're able to prove something about all of them by only doing 2 things, okay? So in logic, if you wanted to write down these 2 kind of steps in like a logical formula, you might say that you have to show that P of 0 is true, and for all m, P of m implies m plus 1, and those 2 things together imply that for all n, P of n. All right, so that's mathematical induction. Let's look at another kind of induction that we're going to be talking about today that's more closely related to program verification and smart contract reasoning. So I want you to imagine this kind of silly game where people are passing the ball between each other. So we've got 4 players, A, B, C, and D. And the rules of this game are fairly boring. The rules are that A always passes to C, C always passes to A, and similarly, B always passes to D, and D always passes to B. Okay, so there's basically these two groups, and they just pass to each other. Okay, and at the beginning, let's say that A starts with the ball, and we want to ask this question: can the ball ever get to player D? Right. So while you're thinking about whether the ball can ever get to player D, I'll play you these fancy PowerPoint animations that I made. Oh, we got one more. Okay, so anyone have any ideas? I mean, it's sort of intuitive that the ball doesn't get to D because A just passes it to C and C passes it to A. So that's kind of obvious. But what if we wanted to show that formally? What if we wanted to prove that no matter how long we play this game, the ball's never going to get to D? Well, we could try to state this property on some kind of mathematical object and then try to use induction. So let's define a sequence of states. And the first state I'm going to call x0, and the state is just going to be what player has the ball right now. So at the beginning of time, A has the ball, so x0 equals A. And then we're going to define the next state, xn plus 1, in terms of the previous state, and it's just defined by a big case analysis. So it says if A has the ball, then in the next state, C has the ball. If B has the ball, then in the next state, D has the ball, and so on. Okay, and these four cases, they encode this graph on the right. And now we have a property that we might want to prove, which is that the ball never reaches D. We can state that property in our formalism by saying for all n, x of n is not equal to D. And now we could try to prove this fact, because this fact is a fact about all numbers, right? It's for all n, something about x of n. So this is a property that's actually amenable to mathematical induction. So we have two things to prove, right? We need to prove that in the base case, x0 is not equal to D. And then we have to prove that whenever you're in a state that's not D, and you take one step to the next state, then you're still not equal to D. Okay, so what about the base case? So in the base case, we have to show that x0 is not equal to D, but we know that x0 is A. So that's pretty easy. The base case works. What about the inductive case? Anyone have any ideas about what we would do in the inductive case? Is it true? So we said the base case works.
Well, it certainly seems true.
Yeah, so the property certainly seems true, right? We already sort of said it's kind of obvious that the ball never reaches D, right? So it's kind of it's really hard to forget that you know something is true while you're trying to prove it, right? But what this inductive technique asks us to do is it says, well, the way to really formally prove something is to show it by induction, and to show it by induction, what you have to do is you have to forget the fact that you've already convinced yourself that it's true, and you have to just prove it. If you're in one state that satisfies your property, and you take a single step, then you're still in a state that satisfies your property. So someone in the chat said something kind of similar, actually. So basically, for every state you can execute, for every state you can reach, there's no way that state is D. And again, that's true, but that's what we're trying to prove, okay? So what's weird about this inductive step here is that this is actually not true. This inductive step is not true, and that doesn't mean the property is not true, but it does mean that the property is not what I'm going to call inductive, okay? So let's look at what's called a counterexample to induction. So I highlight this arrow in red, and what this means is that basically, when we, let me get my pointer back here. So when we're in some state, all we know about xm is that it's not D. Okay. And
gotcha. I see what you're saying.
We don't actually know that it's reachable, and in fact, that's very common in induction proofs. Is you kind of forget the fact that xm is reachable through some sequence of this number of steps, and all induction is asking you to do is, if you don't know it's reachable, but you do know that it satisfies your property, does it still satisfy your property after you take a step? And here's a counterexample. So if we're in state B, then B passes the ball to D, which means in xm plus 1, the ball will be at D, violating our property. Okay. So what we need to do is do what's called strengthening our property. So the way we do that is we prove a different property than the one we started with. And the property that works out well in this case is to prove this stronger property that says for all n, not only is xn not equal to d, but it's also never equal to b. Okay, so this is obviously a stronger property than the one we started with because it implies the original property. If you know that something is not b and not d, then of course it's also not d, right? That's just easy. So it really is a stronger property, but now it's inductive. Okay, now we can prove it without having to know that xm is reachable. Okay, so again, the base case is still easy. A is not B, A is not D. And in the inductive case, if we know that we're not in B and we're not in D, then we must be in either A or C, right? And in that case, we stay inside of our property. We never reach those things. So the way I like to think about this is we have our initial state here, right, A, and then we have some bad state. Maybe I'll circle it in red or something, right? We're trying to show that even when we start execution here, no matter how many steps we take, we never reach this bad state. And what induction really is, what this form of induction really is finding a cut in the graph. It's finding a way to partition the states of the graph so that the initial state is on one side of that partition. All the bad states are on the other side of that partition. And what's the inductiveness check is that no edge crosses from left to right. Okay, because if we had an edge that crossed from left to right, then that would be a state that was potentially reachable from the initial state and potentially could reach the bad state. So if we back up to our previous property, then the cut we were trying to use before, when we're just proving that something is not equal to D, the cut we were using, so circle this in red, the cut we were using was this cut, right? And this edge right here crosses that cut, right? So the cut we had before was not inductive. So I kind of like to think graph theoretically if that's helpful to you. Any questions about inductiveness? I think the takeaway here is that you can have properties that are true, right? We didn't change the property. It was always true that the ball would never reach D, but our proof method required us to prove something stronger in order to reason about this kind of infinite sequence.
Maybe to clarify, like in the case of induction, like you're mentioning this for the set of natural numbers. In this case, we are talking about discrete states. So the induction claim over here seems to be equivalent to a vertex cut problem. So one of the immediate questions I have is like, is this actually scalable?
Right, great question. Yeah, so this is a intentionally very simple first example. And one thing that's strange about this example is there are only finitely many possible states, right? The ball can only be at one of 4 different players. 4 is a very small number. So you can just sort of enumerate all of them and you'd be able to solve this problem very easily. What we're going to look at in just a minute is an example that actually comes from a smart contract where the state space is either infinite or basically infinite for all practical purposes. And so we're going to need techniques that are not based on sort of enumerating all possible states. And the place that scalability comes in is in symbolic reasoning. Okay, so we're not going to try to solve this problem, even though I like to think of it conceptually as a vertex problem, a graph theory problem. We're not going to solve it using graph theoretic techniques exactly because they won't scale to the size of the problems that we want to look at, in particular infinite graphs. We're not even going to be able to iterate over all the states in our graphs. And so what we're going to use instead is this formulation down here that's basically a logical formulation of the problem. And we're going to ship that off to a logic solver that we can talk about more in a couple minutes. But the cool thing about this representation of the problem is that it works well even when things are infinite. The solvers can still perform well because they're not based on enumeration. Great question.
So I have a question as well. Is strengthening any assumptions that you add, or I mean, is it always true that adding the initial conditions would always strengthen sufficiently? But I guess is that why the state space then becomes infinite, or is strengthening refer to adding any clauses here?
Yeah, strengthening. By strengthening, we mean just anything you would do to add stuff to your fact, right? So we started with the fact that x was not equal to x sub n was not equal to d, and we added an additional fact that it was also not equal to b. So anytime you add a fact like that that you didn't actually care about, well, the only thing we cared about was that x was not d. But in order to use this proof technique by induction, we had to strengthen. We had to add a property that we didn't really care about in order to get the property that we did care about. Yeah, and I guess, could you say a little bit more about what you meant by adding the initial conditions?
So the property kind of, in general, if you want to have an inductive property, I guess you said it's like easy to forget the sort of the x0. So if you always end kind of the x0s, then you always know that they're true within your property rule.
Right. So yeah, there's a couple things going on there. So one is that the initial condition in this case is that x0 equals a, but that doesn't mean that it's true that x sub n is always equal to a. Right. So in this case, like the initial condition, it's true. I guess in this system, it's true every other step, but not every step. Right. The ball gets to a every other step. So it's not always true that you can just strengthen by adding your initial condition. You can strengthen by stuff that's true about your initial state, right? So in particular, A is not equal to B, so we can add this strengthened property there. And what I was saying about like it's easy to forget is, in this second case here, it's easy to forget that you kind of already convinced yourself that the property was true, but what you're really being asked to show is that it's preserved by single steps. Cool.
I see.
So, I have a couple other properties that we can look at. Did someone else have a question?
Yeah, I wanted to ask a question regarding this problem. Basically, you solve this problem just by looking at the graph, and
right.
But without looking at the graph, how do you solve this problem? Just based on the conditions of the initial conditions.
Right. So you mean, suppose I didn't show you the picture and I
Right.
just showed you the stuff over here.
Yeah.
How would you know that this is the right thing to add? That's a great question. There's not a great answer to it because this problem is really hard. I mean, this problem is basically equivalent to the program verification problem. It's undecidable in certain instances. So it's not going to have like a perfectly algorithmic solution to it. There's going to be some creativity involved. But I guess what I would say is if you wanted to understand how to do this without looking at the picture, what I would say is I would just attempt the original proof, right? I would attempt to show that the original property was inductive. I would fail. And in fact, we're going to see a demo later of the Certora prover that can give you a counterexample in this case. And it will actually show you the counterexample corresponding to basically this line of the formula that, if the old, or not that line, this line, if the old state was B, then the new state is D. And it would say, hey, like if the old state was B, you could violate your property. And then that would like kind of give you a hint that you need to rule out this state B somehow. And that would maybe give you a hint that X not equals B is a good thing to add to your property. Okay, so a couple other properties of this one. So let's maybe do a little pop quiz here. So the first one, let's see. The first, where's my mouse? There it is. The first one says for all n, if xn is not equal to d, then xn plus 1 is not equal to d. So we can we can basically think of this as saying, you know, in any transition, you don't pass the ball to D, okay, between two steps. It's kind of related to the property that we had before. I think this one is also correct because we already proved actually on the previous slide that we never reach D whatsoever, and this is even weaker. And again, I think this one is not inductive because we have the counterexample where, again, B becomes D.
Without the precondition, though, isn't that proof incorrect?
What do you mean by
Or part of that
precondition?
formula, without the precondition that the ball is starting on A?
Right. So we're kind of taking the definition, the definition of x sub n here. That's the definition that
Okay.
is on the previous slide. So x0 equals A, and xn
Gotcha.
plus 1
We're only looking at the second half of these. Yep. Understood.
Yeah, exactly. Okay, so in the second formula, let's see. Xn is not B and it's not D. Then in the next state, it's not B and it's not D. So again, this is sort of related to our induction property on the previous slide once we strengthened. So this one is also correct. And it's also inductive, right? Because if you know that it's not B and it's not D, then you still know that it's not B and it's not D. Okay, here's an interesting one. Suppose we say for all n, it's either A. If it's either A or C, then it's not D. And notice that I didn't change the index here. So this is a property just of one state. It says, if that state is either A or C, then that state is not D. Okay. So is this true? Yeah, it is true. I would say it's, I drew a really bad check mark there, but I'm actually going to turn that into a V for vacuous. So this is true, but it's sort of true in a boring way because it's true even if we messed up the definition of X, right? This is basically just saying that, you know, the letter A and the letter C are not equal to the letter D, right? There's no actual content in this formula. So this would be an example that's pretty easy to do in real life where you write down the wrong fact and you think you've proved something. You get really excited because you think you proved something, but that proof doesn't actually help you. It doesn't mean anything. Okay, one more property. It's never C. So C was the one that A was passing to. So I think this is just not true, which means it's also not inductive. All right. Any questions about these properties?
My little one. Hello. Hello, little one. Hello.
Oh,
Hello, my love.
how,
Hello, my love.
Let's see. Just got to find the right person there. Okay. So we did this really simple example of 4 states and sort of a very abstract example. But the point of doing that example was basically just to warm up to thinking about smart contract execution really as one of these kind of transition systems or ball games just on a very big graph with kind of weirdly shaped states. Okay, so let's look at a pretty simple smart contract. It's got a mapping that's keeping track of some people's balances. Just to keep things super simple, we're only going to have 2 accounts in the whole system. And in addition to tracking the balances, it's also going to track the total amount across all accounts. And this is a kind of pattern that you would see pretty frequently in a simple like ERC20 token or something. And let's say we have 2 operations on this contract. We have a deposit function that takes an account and an amount to deposit, and it executes that deposit. And we also have a withdraw function that subtracts that amount from the balances. And both of these functions are careful to kind of keep the balances mapping and the total storage field in sync, right? So if you increment one of the balances field, then you also increment the total field. Okay. And what I want to convince you of is that we should be thinking of smart contract execution as one of these transition systems where we're in states and there's kind of this next step kind of idea, and there's some kind of graph, even if we can't compute the whole graph. So, you know, maybe at the beginning of time, the balances are all 0 and the total is also 0, right? We take some steps, somebody calls a public function, we increment Alice's balance, and we increment the total by the same amount. Maybe then we withdraw, we go back to the initial state, or we could take another path, right? We could call a second deposit, maybe on the other count. We also are careful to update the total in that case. Again, we could withdraw, go back. We could even withdraw, you know, back to the initial state here, towards the initial state here. We could do a different withdraw, right? Alice could withdraw. There's all kinds of states, and it gets pretty overwhelming pretty quickly. You know, I guess in the specific case of 2 users and this total field, there's only like 3 numbers you have. Each of the numbers is 256 bits wide in the machine. So there's only, you know, 2 to the 256 cubed states, which is, you know, it's a finite number, but it's not really a usefully finite number. So for all intents and purposes, you know, this graph is infinite. And so we need to use techniques that are kind of geared up to work with this kind of infinity, and that's exactly what induction is good for. So the kind of picture that I want you to have in your head is this is kind of like that graph cut picture that we just drew a couple minutes ago. So we have some initial states where we start execution. We have some bad states that capture the property that we're trying to prove that we don't violate. And execution proceeds, right? We can take one step from the initial states, and these are the states reachable in 1 step. We can take another step, we get states reachable in 2 steps, in 3 steps, and so on. And you know, there's some subspace of the whole state space that consists of all the reachable states. So these are the states that are reachable in any finite number of steps. Okay, and really what we're trying to show is, again, that this blue, largest blue region is separate from the red circle. So we're going to call a system safe if all the reachable states satisfy the property that they are not in the red region. And the way we're going to do that is exactly the way we did it before in the finite case, which is that we're going to find an inductive cut of this infinite graph. Okay, and one way to draw that is basically it's an over approximation, this green kind of arc. It's bigger than all the reachable states. In other words, every reachable state has to be in the green region, and it doesn't overlap with the red circle. Okay, and the way we're going to prove this is exactly by induction. So we're going to have, there's going to be transitions that are happening inside the green property that are reachable, inside the green property that may not be reachable, but that's okay. We can even have transitions that cross the cut right to left. But the one thing that we're not going to allow is that we can't have transitions that cross the cut from left to right. Okay, so this is the key idea of proving inductive invariance. When you try to do this, you run into the same problem that we all ran into, even on the small example, where your property itself is usually not inductive. So the typical case that you're in while you're doing program verification is you've stated some invariant, you're trying to prove it by induction, and you've discovered, or the tool has discovered for you, that there's an edge that crosses the cut from left to right. And so that's a counterexample to induction. It doesn't necessarily mean that your safety property is not true, right? It just means that your invariant right now is not inductive. Okay, so there's a couple reasons this could happen. This could happen because there's a bug in the code, right? So you actually have more transitions or the wrong transitions than you thought you did. You might actually be able to reach somewhere that you didn't expect to be able to reach. So maybe you need to fix the code. There could be a bug in the specification in the safety property, right? Maybe you drew the red circle in the wrong place, or you stated the wrong property. Or there could be just a bug in the inductive invariant, which could happen for a few reasons. The usual one that you're going to see is that it's too weak, right? So we need to strengthen it in order to prove it by induction. But if you've been at it for a while and you've already seen 3 or 4 counterexamples to induction, then maybe you like strengthened a bunch of stuff. You just started throwing stuff in your invariant and you went too far. And so it is possible that you actually go too far and your invariant is too strong. That would mean that it actually doesn't include all the reachable states, in which case you'd have to actually weaken it. So this is like kind of a delicate balancing act to find an inductive invariant. Okay, so in pictures, if you're looking at a counterexample to induction, almost always what you want to do at first is strengthen it. And in pictures, what that looks like is we had this edge that crosses the cut from left to right. And to strengthen it means to move the cut kind of more to the left so that it no longer has this edge crossing it. Okay, if at some point you actually over-strengthened and you had accidentally ruled out a reachable state, then you would need to weaken. And what that would look like pictorially is to move the cut to the right, again, with the same kind of ending effect, which is that the edge doesn't cross, but for two different reasons, right? In this case, it doesn't cross because it starts outside, and in this case, it doesn't cross because it ends inside. Okay, so let's return to our very simple smart contract, and let's take a look at a property that we might want to show. So if we look at the implementation of deposit, what the programmer did here was they, I don't know, they were trying to fit their code on a slide. So they didn't want to use safe math because safe math doesn't fit on a slide. So they just wrote their own overflow check, and their overflow check, is happening on the EVM. So this is being computed in 256-bit bit vector arithmetic. So total plus amount, if that overflows, it's going to wrap around. And if it wraps around, then it will, suddenly be less than amount, which was one of the arguments to plus. So this basically checks that the plus on the last line doesn't overflow. And then the programmer also left us this comment here. And they said, actually, this line doesn't overflow either. Okay, so they're trying to be really clever and only do one overflow check for two different addition operations. Okay, and their thinking here was that, well, the total is always going to be bigger than either of the balances, right? So if we knew for some reason that, all the balances were always less than or equal to total, well, since total is bigger, that means that if we check for overflow on total, that's enough. Because if you don't overflow on a bigger number, then you're definitely not going to overflow on the smaller number. So you don't actually need this second overflow check here. Okay, so let's try to prove this programmer's intuition correct. So let's try to prove that, assuming this require passes, that this addition operation will not overflow. Okay, so we're going to do this by induction. So we're going to try to prove that this thing's not going to overflow. The way we're going to do that is we're going to try to prove by induction that the balances are always less than or equal to total, right? Because if we knew that the balances were always less than or equal to total, then we just kind of convinced ourselves that this addition wouldn't overflow. So really what we need to show is the balances are always less than or equal to total. And we're going to prove that by induction. Okay, so the first question is it true in the base case? I didn't really say what the base case was, but let's assume everything's 0 in the base case. So yes, 0 is less than or equal to 0. So that's easy. So let's look at the induction case. So we're saying, assume you're in an arbitrary state of the contract, not necessarily one that's reachable from the initial state. And now you take a step, okay? And so we knew we were in this arbitrary state where the balances were less than or equal to total. And now we take a step. And the question is, are we still in a state where the balances are less than or equal to total? Okay, and this is not inductive. Can anyone think of a counterexample to induction here? So that would be a pair of states that are connected by like an execution of one of these two functions. And they start in a state where balances are less than or equal to total, but they end in a state where the balances are not less than or equal to total.
Are you talking any state space or any reachable state space?
Yeah, well, so that's a good question. And so if I meant any reachable state, then there would be no counterexample, because I think the programmer was right here, right? I really do think that balances are always less than or equal to total. So in all the reachable states, it's going to be less than or equal to total. So the question is, to prove it by induction, you have to forget what you know about reachability, and you have to show it for any state in the whole state space, even if it's not reachable.
So I guess if you overflow when you calculate total, then that won't be true.
Okay. Interesting. So how would that happen in an execution of this? So let me draw something. So you're saying we could overflow, and then that wouldn't be true anymore. So I think what we want is basically a state where like we've got Alice's balance, we've got Bob's balance, and we've got the total, right? So we're in some state. And then we're going to take either a deposit or a withdraw. Could be either one. And now we're going to be in some new state. Right. And we're going to assume here that our property, let's call it P, is true. And I'm saying that there's a property, or there's a state here where you can make P false. Okay. So I think what Jared was saying about overflow was basically like, if you took a step where overflow occurred, then that could definitely cause you to violate it, right? So like if total overflowed, then like we could overflow total to 0 or like some really small number, and that might be less than some of the balances. But the thing is, that's not a step of this contract, right? That's not how contract execution works, right? Because like the whole transaction will just abort if this require clause is false. And I think this require clause correctly checks that total doesn't overflow. So I think it's impossible that during a step that actually succeeds in like committing the EVM transaction, that it's impossible that total would actually overflow, which means it would have had to overflow already, in which case total would already not be less than equal to greater than or equal to balances. So I think that's not a counter example to induction. There are a couple things in the chat. So yeah, so it looks like some other people were talking about overflow. What about if the initial state does not equal to the total balances? Yeah, exactly. So, okay, so the idea is that what if A plus B is not equal to T here? So I don't know, let's do some example. Let's say Alice has 10, Bob has 5, but this, for some reason, the total is only 10. Okay, so the total is clearly wrong, right? This is not possible. It's not a reachable state, but it is a state. And what would happen if we took a withdraw step here, right, where we allowed, let's say, Alice to withdraw 10, right? If Alice withdrew 10, then we would be in a state where Alice's balance is 0. Withdraw, right, it decrements total, so total would be 0, and Bob's balance would still be 5, right? And now Bob's balance is strictly greater than the total. Even though we started in a state that satisfied these two properties, we ended in a state that violated them. Okay, and actually, this is a great example because, and the intuition that came from the chat is perfect because, the intuition behind this example is let's find a state that's kind of bogus, right? Because Alice's balance plus Bob's balance is not equal to total. So that kind of like immediately just like yells in our face, what's the strengthening that we need to do, right? The strengthening we need to do is to keep track of this invariance that balances, like Alice's balance plus Bob's balance is equal to total. Okay, so first of all, let's make sure that this invariant really is stronger than our original invariant. So we wanted to know that both the balances were less than or equal to total. And let's say if we knew that balances, like Alice's balance plus Bob's balance is equal to total, would that imply our original property? And I think the answer is yes, assuming that this addition doesn't overflow. Okay, so let's say maybe we do this addition in math instead of on the machine. Okay, so it really is a stronger invariant. And now we have to reason by induction. Okay, so now we ask ourselves the same question. Is there any state, right? We have some state, ABT, right? And then some transition to a new state, ABT. that satisfies this property, but violates it in the post state. So we're starting a state that satisfies a property, we take some step, and now we're in a state that violates the property. So let's just think about that for a second, see if we can come up with another counterexample to induction. Yeah, so thinking about it, there is no counterexample to induction. I think it's inductive, right? This property is inductive. So how would we convince ourselves that this property is inductive? Well, one way to do that is to try to write out kind of a proof. So first of all, let's write out a proof that our invariant implies that things don't overflow. So we wanted to show that we didn't need the second overflow check. So what that really boils down to is that Alice's balance plus the amount is not going to overflow, which we could write like in math. If this was a mathematical addition and not a machine addition, we could write it as this inequality that basically says, whatever the maximum bit vector representable in the EVM, these two numbers added up are less than or equal to that. So that follows because we're going to have our requirement in the code that actually guarantees that the bit vector addition doesn't overflow. We're going to have our inductive invariant. We're going to prove it inductive in just 1 second, but we already convinced ourselves. So if we knew that, that tells us that balances of Alice is less than or equal to total. And we know that total doesn't overflow, and that tells us that balances of Alice doesn't overflow, right? So this is just a recap of that argument that shows that overflow will not occur in the second addition because of this invariant. Okay, so the more interesting thing is how do we prove that this thing is really inductive? Well, to do that, we kind of have to write out what the code does in math. So we're going to say, okay, we know we're in a state where we're satisfying our property P, right? So Alice's balance plus Bob's balance is equal to total. And then we're going to take a step. In this case, let's say we're working on the case of the proof where we're depositing some amount into Alice's account. So that means that the new balance for Alice's account is going to be whatever the old balance was plus the amount being deposited. And similarly, the code is very careful to also increment total by that same amount. And now we need to show that balances, like our property P is still true. So Alice's balance plus Bob's balance is still equal to total in the new state. And of course, Bob's balance didn't change during this transaction. Okay, and if you assume that all of these additions and equal signs are happening in math land instead of in overflow land, then this is basically just substitute everything in and it balances out, right? Basically, we're adding something to this side of the equation because we're adding amount to balances to Alice's balance, but we're also adding amount to this side of the equation, so it all balances out. No pun intended. Okay. So what's cool about this is that you can also, so I don't know about you, but like these kind of details are really hard to track. And that was a really simple program. And we had to write out like a whole slide of equations just to do that. So it's nice to have some tool support to do this for you. So one of the nice things that you can do in the Certora prover is you can state and prove invariants like this. Okay, so we're gonna actually switch to some code now. So let's go ahead and look at, do you see my VS Code?
Yes, indeed.
Okay, perfect. So we're going to look at this invariant in code. So here is how you would state that in our prover. So we've got this bank contract. I typed it in here. We've got our, let's see, we've got our deposit and our withdraw. And we've got the same state that I showed you on the slides. We're going to come back to this transfer function in just a second. And then I just added a bunch of view functions to let us get the different parts of the state really easily. And so now in our specification file, which we write on the side of the contract, we can state this invariant that we talked about. So we can say, we want to know that Alice's balance is less than or equal to total. We want to know that Bob's balance is less than or equal to total. And if we, let's see here, I think if I do this, and then I do this, and then I do that. So if we run this tool on this example, what it's going to tell us is that smaller total, which was the name of that invariant, is actually not true. Let's ignore the transfer problem for just a second. Let's look at withdraw. And what withdraw does is it's basically the counterexample that we looked at. So basically, we have to like read through here to figure out exactly what the state was. But essentially, we're going to call withdraw, and that's going to cause us to have a counterexample to induction. So the way that the Certora prover, when you say invariant in your file, the Certora prover attempts to prove that by induction. You and I both know that this invariant actually is true, but the Certora prover will give you an error on it because it's not inductive. And the way the Certora prover tries to prove invariance is by induction. Okay, so what you have to do is you have to do exactly what we did on the slides, and you have to strengthen your property. So it says that the total is equal to the sum of the two balances. Okay, and if we go back to our report here and look at that invariant, we would expect to see this in green. Okay, and it's actually not in green. And the reason is I added a function. So it passes both the deposit and the withdraw function. So if I didn't have this transfer function, it would be inductive. So in the last couple of minutes, let's just take a look at this transfer function because it's kind of interesting. So this is another kind of simplified thing that you would see in an ERC20 contract where we're trying to transfer some amount from some account to some other account. And this code is written in a kind of a strange way to demonstrate a bug. So what we're going to do is compute the new balances for both the source and the destination account in advance. So we're going to say the new from balance is going to be the old from balance minus amount. The new to balance is going to be the old to balance plus amount. And then we're going to write back both of those values. And it turns out that this is just wrong. This code is not right. And it's not right when from is equal to 2. Okay, so what if we look at the report, we'll actually see this in the counterexample to this. So a little hard to read in this line here, but basically transfer 111. If we look at the signature for transfer, right, the first two arguments are the accounts. So basically this is saying you're transferring from account 1 to account 1. So basically they're equal to each other. So if we put require from not equal to 2 here, and then rerun that, it'll take it just a couple seconds, but we should be able to see a bunch of green rows in our report at the end of the day. While that's running, if anyone has questions about the code example, now's a good time to talk about them. If not, we'll just take a look at this. These pretty green rows. Okay, so you can see that the first line is still red. That's our non-inductive invariant. And our inductive invariant now has green in all the cases, including the transfer case, once we add that requires clause. Okay, so that's just a super simple like code example of how this stuff actually matters. So just to leave you with sort of some takeaway messages here, let me get back to my slides. We looked at all of this, blah, blah, blah. Oh, there was one example we wanted to just mention. This stuff is actually like, at least in my view, like this is a lot of bugs you can find this way. So if you're reasoning by induction, you're able to find like these counterexamples to induction. You're able to find properties that can actually be exploited, which is pretty interesting. So I don't know. It's the way I think about things, at least. I don't know. Shelley, did you want to say anything more about this this example?
I think some people are already familiar with this happening in numerous places in DeFi by this point. Right.
It's sort of a template for an example in some sense. Okay, let me just end on my conclusion slide. Blah, blah, blah. Okay, so I think the main thing I wanted to introduce to you today was this idea that you can have properties of your code that are true, but not inductive. Okay, and it's actually really hard to tell the difference if you're not using, some kind of verification technology. It's first of all, it's really hard to tell between true properties and false properties. But really the only way that verification technology can handle infinite state spaces is to reason by induction, which means it's not good enough for your specification to be true. You also need to know that your specification is inductive. And often what happens is there's a bug, either in the code or in the spec, that actually makes it not true. But the way you find that bug is by trying to prove it by induction. So if you don't have an inductive invariant, then you can't even get off the ground. So the way to think about inductiveness from a smart contract perspective, like what are the edges in our graph? They're basically the different transactions that might happen on chain when people call into the contract. So the way I think about it is, inductiveness means that your property is preserved by all the public functions that are available in your contract. And that's how our invariant feature works in the Certora prover. It reasons inductively, and that means that it has pros and cons. But the nice thing is it can reason about infinite state spaces and give you a guarantee, even when there are just an obscene number of reachable states. We can still get a complete guarantee that not a single one of them has a violation. And the nice thing is when your property is wrong, you get these counterexamples, which admittedly are a bit of an art to read, but they do have the information you need in them to kind of figure out what went wrong. So I'll leave it there. Happy to stick around and answer any questions that people have, or just hang out. But thanks again for coming, and we'll see you in the next one.
Hey, James, just a question. What's kind of like, maybe you can give us a little intuition about how this Certora prover finds counterexamples?
Sure. Yeah. Probably the easiest way to do that is to draw a picture. I'm actually going to draw it over here. So the way I think about this, you've got some. So this presentation was at a pretty high level. So we were kind of when we drew pictures on the slides, we were kind of hand waving the connection between the code and the pictures on the slides. The way that actually works is you have a .solve file, you have your contract, you have a .spec file, which is where you write the property that you want to show, and you send those to the Certora prover, which does magical things that I'll explain in just a second. And that basically gives you two possible outcomes. It gives you a nice big green check mark, or it gives you a red X. And if it gives you a red X, then it gives you some kind of counterexample. Okay, so the way this box works internally is it's actually very similar to a compiler. Okay, so what it does is it translates, it uses the Solidity compiler to translate the Solidity code into EVM bytecode. So we get the bytecode. It takes this spec file and it combines it with the bytecode to find basically, we have the meaning of the program is expressed in bytecode. We have the property that we're trying to prove is expressed in the specification. And we take those two things together, and there's a formal process called verification condition generation, or VC generation, which takes those two things. So I don't know how I'm going to draw this. Why don't I just make more arrows? That's going to generate a verification condition, which is it's a formula in logic that encodes simultaneously the meaning of the program. So like, what does the code actually do? In PL, in programming languages, we call that the semantics of the program. And it also takes the property that you're proving, or that you want to prove, and it compiles those two things together into a logical formula. And these logical formulas, it's a really exciting breakthrough in the last 15 years, which is a long time in industry, but a short time in academia. So just in the last 15 years or so, academia has finally figured out good automated solvers for solving these formulas. So then what we do, let me erase my fee here. We send this out to 3 or 4 different solvers. All of them are open source. CVC4 is one of them. Vampire is another one. Z3 is one. So we ship this formula to several off-the-shelf logic solvers. These guys don't know anything about Solidity or EVM, right? So they just know how to do logic problems. So we compile our problem into a logic problem, and then they tell us these answers, right? So they either tell us that the logical formula is guaranteed to be true, or they give us a counterexample. And then we do a little bit of, we have to do this kind of like back translation step. We take the logic counterexample and we translate it kind of backwards up from logic back into kind of programming speak so that you can at least kind of read it in the reports.
How do you
Yes,
go
that's
about,
basically how it works.
pardon me, how do you go about generating all the potential problem spaces, basically? Because you mentioned, yeah, because that that seems to be kind of the crux here. It's like the problems that you don't think about that are going to cause you problems.
Right. Yeah. So great question. So for sure, if like any of these arrows on this drawing required like enumerating states, this whole thing would never work. It wouldn't even work on the tiny code example with just 3 UNT256s because there's just too many to enumerate. So the cool thing about these techniques is they don't involve enumerating states. Okay, so the way we get around that, the reason we're able to avoid enumerating states is that in this logic formula here, we basically have logical variables that that represent the state symbolically. Okay, so just like in math, like if somebody asks you to prove that you know, a plus b is equal to b plus a, right? You don't have to do that proof by enumerating all integers, right? Instead, you can do that proof by induction or by some other process that doesn't involve enumeration. And so inside these solvers, they're not solving it by enumerating states. They're solving it using logical techniques. And so actually none of the arrows anywhere on this slide involve enumerating the different states. What we do have to do is just be really careful that we encode the meaning of the program correctly, right? So like EVM has lots of different bytecode instructions. Some of them are really weird and they're challenging to encode into logic. It's especially challenging to encode them into logic in a way that the solvers can actually solve it. So there are plenty of challenges here, but yeah, there's absolutely no state enumeration happening anywhere on this whole picture.
I guess the reason that I'm confused still is because in the Certora like UI, you're clearly showing states that failed.
Yeah, so that's the magic. That's the magic of these guys, is that they also don't do state enumeration, and yet they give you counterexamples. So our counterexamples are not magic. They come from these open source logic solver tools that give us counterexamples. And the way those work are, it's a logical flavor of reasoning where they look at the formula, they do symbolic manipulations on the formula. Either they convince themselves that the formula is always true, or they convince themselves that it's false. And if it's false, they'll give you a specific value for every one of your variables in order to make it false. So all that magic is happening inside these solvers.
Ah, I see. Thanks.
That's a really interesting topic. I think we actually have a lecture about that. Don't we, Muli? Somewhere? Is it recorded? I don't remember.
Yes, it's on our website, right? Shelly, we have one lecture about it, and there are many other lectures by other teams, by other people. Yeah.
Yeah, I think we have something about something more specific.
Yeah, we have more technical talk on the, but it's not about induction. It's about this idea of constraint solving. I mean, these are complementary.
Right. I'll see if I can find it. But yeah, there's a talk on how these logic solvers work internally.
Yes, maybe
but
just
yeah, super interesting topic because they they do definitely feel like magic. I encourage you to look into these if you're curious. You know, it's very far away from programming. You know, they have no features related to programming. It's pure logic, but it's really magical what they can do if you can express your problem as a logic problem.
Right. I have a question. How do you actually, what exactly is the intuition behind finding this induction claims and invariance? So like, for the bank example is still fairly straightforward. But let's say, for example, like the flash loan attacks and the B, like I can't remember, there was one exploit that you mentioned that was shown on the slides previously. Like typically these contracts are way much more complicated. So like on a practical basis, when you're developing these smart contracts and writing the specs, how do you like go about finding this inductive claims in an intuitive way? Because it can be quite non-obvious.
Right. Yeah. So I don't think anyone, even experts, starts with inductive properties. So what you almost always do is you start with what we were drawing on the slides is like the red circle, right? The thing that you don't want to happen. And you ask the tool, like if I was using the Certora prover, you know, I just write down that property and it would probably not be inductive. So I would get a counterexample. And then you have to look at the counterexample and think about, you know, what I would need to do to strengthen it to make it inductive. So are you more interested in coming up with the red circles or in coming up with the strengthened properties after the counterexamples?
So like that being said, does it make more sense to like consider like the bad state spaces first as like when you're coming up in this inductive proofs? So so one of the key problems about the flash loan attacks, they rely on price feeds and unreliable oracles, like for example curve vault. So some of the attacks rely on mispricing data, which you do by flash loans from like either Aave or like Uniswap, which would then basically kind of change the price data, and then you kind of do like an exploit by drawing out the funds because of this mispricing. So some of the key problems right now that I see is that the contracts are not necessarily yours. It could be due to some other protocol, due to interoperability and solid on Ethereum,
Right.
which makes the space actually quite hard to figure out. But I guess maybe on your own side, you can probably like secure your own contracts, but because of the interoperability with the other contracts, it's kind of hard to secure those other contracts which you're interacting with. So like how do you actually go about this?
Right. So this is interesting. This is related to a really kind of deep issue in any sort of verification project, which is modeling your environment. Which, if you're more of a security-minded person, you might think of this as kind of like formalized threat modeling. So basically, thinking about, you know, what are the possible scenarios that I'm interested in defending myself from, and the one you mentioned is really interesting, right? Calling into code that you didn't write, and you know you're relying on some behavior of that code, and it's not your code. So then I think you basically have two options. The question is, I think the first question really is, can that code be upgraded, right? Can it change out from under you? And if it can be upgraded, then your life is even harder. If it is never going to be upgraded, or not without you kind of approving it, or at least noticing before it happens, if you're in that easier case, then what you could do is actually just fetch the bytecode from like the deployed bytecode on chain. And because our tool operates at the bytecode level, you know, you could just plug that in and you could just verify your code against their code without really even knowing how they wrote it, even if you don't have the Solidity source code. But I think the even harder problem is what happens when they can upgrade it without telling you, and then your life is harder. In order to get a guarantee, right, you probably start by verifying yourself against the current version, but then maybe you want to be robust against upgrades. So you want to kind of find, are there some like minimal set of properties that I need to know about the contract that I'm calling, such that if I knew those properties, then my code would be correct. And then maybe you could write some kind of monitoring infrastructure that would, observe upgrades and check whether those properties are still true, or maybe monitor them dynamically and check that, inside of a particular transaction, those key properties are never violated. So there are some options there for verification, but yeah, it's definitely harder, calling into dependencies that you don't own. Yeah.
Okay, thanks.
Yep.
So like what I understand from that statement is that you're going to find some invariants for the external contract calls also.
Mhm.
Like for example, when you're mentioning like the kind of restricted properties, that will also constitute a kind of invariant for those contracts.
That's right.
So like you would also have so to kind of model this whole system, like you can't just model the invariance for your own systems. Like it's also best to model the invariance for the contracts that you could interact with, and
That's
then
right.
and basically run the approval on this whole entire system.
Right. So you have two options there. You could run it on the whole system, and that would check everything. That would check that the other contracts, first of all, satisfy their invariance, and that that's enough to give you your contracts satisfy that your invariance. Or you could do something kind of interesting. You could run the tool only assuming the invariance about the other contract, but nothing about the code. So you would basically say, suppose I don't have access to the code I'm calling, and I only know that it satisfies these invariants. Can I prove that no matter what the code does, if the code satisfies these invariants, then my code is correct? And that would kind of let you be robust against changes that they make to the code, as long as those changes still respect the invariants. You're not like depending on implementation details of the current version.
Okay, understood.
So one question is, in practical terms, in using Certora, I know you said it can only do inductive proofs, and you showed starting with the property you want to be true and then strengthening or weakening that to get to something that's inductive.
Right.
Besides that approach, is there anything additional that's helpful in writing the specifications that has to do with inductions? Like I didn't realize that the proofs had to be inductive. I just wrote specifications and cite,
right.
See what happens.
Yeah.
But
So it depends on the kind of stuff you're trying to prove. Like some properties, you can get pretty far actually in the tool without ever realizing that you're actually doing proofs by induction. It's really once you get to like more advanced specifications that involve kind of like tracking some like coherence relationship across multiple different pieces of the state. That's when you start needing to think inductively. In terms of like other like things that help with writing specifications, like I think spec writing is actually really hard. So I'm not sure there's like a silver bullet there. You kind of have to sit down and think about what keeps you up at night, right? Like what do you worry about going wrong in your contract, and then you try to write down a property that says that thing doesn't happen, and then you might need to strengthen it if it's not inductive. But I'm not sure I have any like other like concrete tips for spec writing.
fair enough. Thanks.
Cool. Any lingering questions folks had? if not, I think we can call it a day there. Thanks again, everyone, for coming and staying for this discussion part. Yeah, hope the Certora prover finds inductive invariance for you.
Have a great one.
See ya.
Thanks.
Thank you so much.